So today I want to talk about arithmetic series. And those are sums that look like, for example, 7 plus 11 plus 15 plus 19 plus 23 plus 27, for example. And the key idea of an arithmetic series or an arithmetic sum is that the numbers that I keep adding together are the same distance apart. So the common difference here is 4. And that means in general, if I want to write down a general arithmetic series, I can write it as a, that's the starting point, plus, and then the next number, which is a plus d, where d is the common difference, and then a plus 2d, and so on, up until the last term, which I'm going to call a plus n minus 1d, because that way n denotes the total number of terms in the series. So you can count 1, 2, 3, 4, all the way up to n. Now, what I want to show is the following formula for the sum of an arithmetic series. So I can write it in sigma notation, so that would be the sum k equals 1 to n, the n terms of the series, a plus k minus 1 d. So it's easy to check that when k equals 1, we get a, when k equals 2, we get a plus d, and all the way up to when k equals n, we get a plus n minus 1d. And the claim is that this sum, the sum of any arithmetic series, can be given by the formula n times 2a plus n minus 1d over 2. So this is what we want to show. Now, how would you come up with such a formula? Well, that's not what this video is about. And as a hint, you want to sort of look at adding the first and the last term and the second last term. That can give you a hint for how you might come up with this formula. But the point of this video is to prove that this formula is correct and to use it to illustrate mathematical induction. So this is going to be a part of the playlist on mathematical induction, and so we're going to use induction to prove this claim. So the proof is by induction. And the way that induction works is we start with our base case, n equals 1. So at n equals 1, that's saying, what if you have an arithmetic sum, an arithmetic series, with only one term? So then that just looks like a. Then I want to show that the sum of that, which is just a, is given by this formula. So n equals 1, 2a, and then n minus 1 is 0, so that's 0d over 2. So this is what we want to show in the base case. And indeed, this is true because if I simplify the right-hand side, I just get 2a over 2, which is equal to a. Now the base case is taken care of. We move on to the inductive step. And as usual, the inductive step says assume true for n and prove for n plus 1. In other words, I'm going to assume that that this formula is true. So now what we want to consider is, what about a sum with n plus 1 terms? So that would look like the sum k equals 1 to n plus 1 of a plus k minus 1d. And what we want to show is that that must be equal to the corresponding formula, but now with n plus 1 in place of n. So n plus 1 times 2a plus, now this becomes n, nd divided by 2, which if I multiply this out, is equal to 2an plus n squared d plus 2a plus nd over 2. So this is kind of a mess, right? But the question is, can we show that this sum really does equal this expression? And the way that we're going to approach it is by using the inductive assumption. We're going to use the assumption that the formula is true for a sum of up to n terms. So we can write again our sum of n plus 1 terms. So sum of k equals 1 to n plus 1, a plus k minus 1d. And realize that a sum of n plus 1 terms can be rewritten as the sum of the first n terms plus the very last term. And the very last term here looks like a plus nd. Make sure we keep this separate. And now we can use our induction hypothesis, this assumption that the formula holds for n, and apply it to this sum, which has n terms in it. And that gives us n times 2a plus n minus 1d over 2, plus, and since I'm going to add these, I'll make a common denominator, 2a plus 2nd over 2. So if I multiply this out, I get 2an plus n squared d minus nd plus 2a plus 2nd, just an algebra, all over 2. And that gives me 2an plus n squared d plus 2a plus nd over 2, which is exactly what I was supposed to get. So what we've shown is that if the formula holds for a sum up to n terms, then it must also hold for a sum up to n plus 1 terms. And since we know it holds for a sum of just 1 term, we can get all the way up to holding for any sum no matter how long it is, using mathematical induction.